Okay, so today we're going to talk about analyzing data, and let me just share my screen here. Great, close this up. And all right, so we're going to talk about different ways of analyzing data. So we're going to look at analyzing means in different ways. So we've got the one sample means, we've got the matched pairs, and then finally the two sample means. And then we'll move on to analyzing proportions using the Z-test. So we'll look at one sample proportions and two sample proportions. And then we'll look at just some simple regression where we're analyzing the relationship between two numerical variables. Okay, so we're going to keep using the CDC data. So we can just copy and paste that. I've cheated. I've got my, not cheated, I Martha Stewarted. I've got my blank RMD file ready to go here. So I'm going to run this CDC data set, bring it in. Remember, it's pretty big, so we have to wait a little bit. Still thinking. There we go. It looks the same as it has in the past, so nothing's changed. And so what's nice is we know a lot of these variables now. So for means, when we analyze them, we use a t-test, and so we're going to use the same t.test command, just it's how we set up the arguments inside that are going to change. So we'll start by looking at just the base command for a one sample t-test. So we use the t.test, and then it takes the column or the variable that you want to analyze, and then we need to tell it what our hypothesized mean is, right? So for one sample mean, we have some sample information that we want to compare to some hypothesized mean. And so, for example, if we want to look at the age variable and I ask you, is there evidence that the mean age is different from 30, then the command we would run is just t.test, and then we want to test the age variable, and is it different from u equal to 30? Okay. So this is the bare minimum of what a t.test for one sample needs. So if we run this, then we get, mine shows up here, yours probably shows up here, but I'm old school, so I shut that off. But your output might come up down here. But so I get the same stuff down here. So we get a t of 123.95. That's pretty big. And a p-value that is itty-bitty, 2.2 times 10 to the negative 16. So it's safe to say that we can reject the null hypothesis that the mean is equal to 30 and say that the mean is not equal to 30. Notice that by default we do a two-sided test. Okay? And so we can change that as one of our arguments. So we can add arguments like the alternative. We can add, okay, well, we suspect that maybe alternative is, and then in quotes, we have, I've listed the options in the instructions. We have two-sided, which is the default, less or greater. So we suspect that maybe it's greater just by looking at our confidence interval that it gives us. So 44.83 to 45.31. And then it also gives us just the sample mean for the age variable in our data set. So if we run this, one thing that I want to show you is that in order to produce a confidence interval, we have to have a two-sided alternative. Okay, so either the default or specifying that it's two-sided. Otherwise, it'll pretend that it doesn't know the upper bound or the lower bound, I think, if it's less. So if we want a confidence interval, we have to either leave it as default or specify that the alternative is two-sided. And so here, I'll just highlight the options that I've listed for you. If we want to change the confidence interval, so here by default it gives us a 95% confidence interval. If we want to change it to get maybe a 90% confidence interval, we change the conf.level argument to be 0.90. So now if we run that, we see that, okay, nothing's really changed except for our confidence interval is now a 90% confidence interval. So these additional arguments, right, they're optional, but they apply to all of the t-dot tests that we're about to do. So we can change the confidence level and we can change the alternative if we want to. But for us, we'll just look at the base arguments. So that's our one sample t-test. Moving on to our matched pairs, it takes data in the form of t-dot test and then your first column, comma, your second column, and then we need to tell it that paired equals true, meaning just look at these columns as pairs, making them matched pairs. And so let's say, let's analyze the difference in the respondent's actual weight versus their desired weight. Is there a significant difference between the two? So if we want to know if there's a difference, we have a two-sided test. Right? And so just copying this command here and running it here. Right? So we want to look at, okay, their actual weight, their desired weight, and then saying, okay, compare these across each individual. Is there a difference between the two? And so what's interesting is that we get a mean of the differences is 14.591, and our 95% confidence interval, so we're 95% confident that the interval from 14.26 to 14.92 captures the true difference in the weight and the desired weight for the population. To me, that's interesting because that's such a tight interval. So everyone seems to, or overall, 14 pounds seems to be the goal loss weight. I don't know, just kind of a fun thing. Again, we're going to reject the null hypothesis just because we've got an itty-bitty p-value again, and with a difference of 14.6 essentially, yeah, we would say that that's different from 0. Right? And turns out it's significantly different from 0. So we have our first column or second column, and then paired equals true for a matched pairs. Looking at our two sample t-test, we actually have two options for doing a two sample t-test, and that's because of the two different ways that we could set up our data. Right, so the first way that we could set up our data is just to have one numeric variable and then a categorical variable as our second column. And so if we want to know, is there a difference in the weights depending on whether the person has smoked 100 cigarettes in their lifetime or not, right? That's the smoke 100 variable that we looked at before, right? And it's either 0 or 1, so that's a categorical variable. And so the first option that we have is just to take the t-dot test and do y tilde. Remember, I read the tilde, which is the little squiggly, as by, so y by x, okay, where y is numeric and x is binary. Binary meaning just two options, 0, 1, yes, no, male, female. Okay. So if we want to test if there's a difference in the weights of people who have smoked 100 cigarettes in their lifetime and those who haven't, then we use the weight by the smoke 100. So we've still got a small p-value, right? We've got a t of negative 7.7541, which is still really large. So we're going to reject the null hypothesis. And it looks like, right? So we've got a negative confidence interval, so both of those values are below 0, right? Which means, again, we can reject the null hypothesis that the difference is 0 between the two groups, and say, because it's going to go smoke 100, here's a little detective work, right? So smoke 100 is a list of zeros and ones, so it's going to do the zeros minus the ones, and so the weight, right, the difference in the weights, if it's negative, is just saying that, okay, if you haven't smoked 100 cigarettes, you weigh less than those who have smoked 100 cigarettes. I don't expect you to go that deep, but that's the inner workings. Another option for our two-sample test is if we just have two columns in our data set that we want to compare, right? They're two independent samples, potentially with different sample sizes. And so if we just have two different columns that we want to compare the means of, then we can use the t-dot test and then first column, second column. Notice that this is the same setup as for matched pairs, except we don't say paired equals true. So the default setup is that you have two independent samples, and then if you have matched pairs, then you say paired equals true. And so we don't have a variable or two variables that are suitable for this, so I made two variables. And so I made a subset of the male data and a subset of the female data, and I'm going to compare the weights of the two groups. Right? So now we have two different sample sizes, as we've seen for our males and females, but that's okay. So first we have to create these subsets. I'll just copy this whole chunk and run through them one by one. So I'm going to create this male data, which has 9,569 observations. And then I'm going to run this female data, 10,431 observations. And if we do the t-dot test, notice that I've changed it to M data, right? The male data, so go to the male data set and pull out the weight variable, and then go to the female data set and pull out its weight variable and compare those means is what the t-dot test does. So if we run this, again, yeah, there's a difference in the mean weights of the males and the females, right? And just because of the order that we've listed them, so M data and then F data, it's going to do M data minus F data. And so a positive interval just tells us that we have a higher weight in the male data than in the female data, which is not surprising. None of this will be surprising. So, we're just confirming what we already suspect most of the time. So the difference in the male and female weights is significantly different from 0. So that's our t-dot test. So 3 options for your lab report. You're only going to do one t-dot test, so just depending on your data, whichever one is appropriate, then you just have to run that t-dot test. Okay. Moving on to proportions. Okay. Proportions, remember, have to do with categorical data, and so of course the prop.test, test, which is the one that we're going to use, requires that we know how many are in each category, right? And then we'll be able to compare the proportions in each category. One sample proportions, right? We just take the sample proportions and compare it to some hypothesized proportion, right? So if we want to know, is there evidence that 85% of the population has a health plan? And so I just have a little note here that if we're testing, if more than 85% of the population has a health plan, we would require a one-sided test, right? But I'm just showing you the bare minimum, and again, you can change the alternative, you can change the confidence level in the prop.test as well. So, but because I'm just showing you the bare minimum here, we just want to know, is the sample proportion different from 85% or 0.85? So first we need to know, okay, well, how many people in our sample have a health plan? So if we run this table, right, we learned last day, we can see how many have a health plan and how many don't. So 2,524 respondents don't have a health plan, whereas 17,476 do have a health plan. And so now the prop.test command uses, oh, here it is, prop.test takes a value of x, that's the number of successes, the value of n, your overall sample size, and your p0, which is your hypothesized proportion. So for us, we want to know if 17,476 out of 20,000, is that significantly different from the hypothesized proportion of 0.85? So copy, paste, and run it. Okay, so again, we've got probably the easiest way to look at this is through our confidence interval, right? Our confidence interval is between 86.9 and 87.8, which are both over 85, and so we can reject the null hypothesis that the proportions are the same. Or sorry, that the proportion is the same as 0.85, sorry. Okay. And we suspect that it's actually higher than 85% just because of the sample proportion being higher than 85%. The sample proportion is 87.38%. Okay. So if we want to test two proportions, we take the same setup, except now we need to know how many successes are in the first group, how many successes in the second group, and then we need to know the sample sizes for each of those two groups. For two sample proportions, we're comparing the proportions in each of these groups, and so we don't have to set up our hypothesized proportion because our hypothesis is that they're the same, and then we test to see if they are the same or not. So let's take it one step further and say that, okay, if we want to know if there's a difference in the proportion of males and females with a health plan, so we first need to know how many males and females have a health plan, right? And then we need to know out of a total number of males and females. So we already know the total number of males and females, but I've included the table just in case. Let's just copy this over before we talk about it. So here, right, if we make a table of the health plan and then comma gender, then we have zeros and ones in the rows, and that's just saying if the person has a health plan or they don't. Has a health plan, 1, don't, 0, and then whether they're male and female. Right, so we've seen this type of table before, and so now we know that, okay, the number of males with a health plan is 8,314. The number of females with a health plan is 9,162. So those would be our number of successes. And so we use this C, which is the concatenate, which we saw briefly in lab 1, or earlier, maybe lab 2. But it's just a way to feed a list of information to R. So now we say X is going to be a list, so concatenate 8,314, right, the number of successes for the males, and 9,162, the number of successes for the females. And then our N, our sample sizes, are going to be the number of males and females overall in our data set. And I just got those from the table. We could have grabbed those from a number of places, right? The number of males is the same as our M data size, and the number of females is the same as our F data size. So we have lots of ways of finding those sample sizes. But I just made the table of gender to see how many are in each group. Okay. So there's our core means and proportions analyses. So finally, we're going to talk about linear models for simple regression. And so regression is basically where we're plotting a line of best fit. Right? And so the first thing that we're going to do, and we will only talk about fitting linear models. And so what we have to have is a straight line relationship in order for it to be modeled by a straight line. So what we do is we're going to use our plot command, and I think the example I made up was, we're going to look at the weight as the response variable and the height as the explanatory variable, right? So it's reasonable to think that the height of a person is a good predictor of their weight. Seems reasonable enough. So first thing I'm going to do is plot it. And notice that I'm going to use so last lab we talked about our 3 different ways of plotting a scatter plot. I'm going to use the y tilde x, right, where we have the response variable y by x. And that's only because that's the same format that I'll use to fit my straight line later. So I'm going to use this plot command and just have a look and see if fitting it with a, oops, got squished here. If using a straight line to model this relationship is reasonable. Got a little squished, it's okay. There we go. Seems reasonable that if we were to model this, right, or describe it, there's some linearity here, right? So we're going to fit a straight line, a line of best fit. And what that line is going to help us do is just, if we have some height, we'll be able to predict their weight. Remember, the whole point of a regression line is to be able to predict values of y. So to fit a linear model, we use the lm command. And like I said, inside the arguments are the same as the plot command, where we have the response variable by the explanatory variable x. What you want to do is you want to save it as something. So I've called it mod 1. Often if you're doing regression analyses, you end up doing quite a few models. So you start at mod 1, mod 2, mod 3, etc. So you can name them something funner, but I've just stuck to boring mod 1. Okay. And so if we run this, nothing happens down here, but that's because it's generated this mod 1, so it keeps all the information, and it looks all nasty up here. So it keeps all that information about the model in mod 1. Okay. It'll keep things like what are the residuals, it'll keep things like the slope and the intercept of our least squares regression line. It keeps all that information. What's your R squared? Okay. So to see a summary of mod 1, which is what we're interested in, we'll use the summary command. So now we can run a summary of mod 1, and we get down here. So it'll tell us what the model is, right? Weight by height. The residuals, which we won't talk about here, but it'll give you a 5-number summary of the residuals. And most importantly, out of all of this, it gives us the coefficients. And so the coefficients for the intercept is just the intercept of your model, and the coefficient of the height, remember height is your x variable, right? So the coefficient of x is your slope. So it gives you the intercept and your slope of your regression line, right? Or your linear model. It also gives you the standard error and the t-value and some p-values, but we won't talk about those here. Then it gives you some more information. The key part that we're going to be pulling from here is this multiple r squared, and that's the r squared that we probably talked about in class, or will talk about in class, and it just tells you the percentage of variability that's captured by this line. Okay. So if you're reporting, then you'll want to talk about what's your slope, what's your intercept, and what's your r squared at a minimum. So what if we want to plot this line that we've made, right? This line has a slope and an intercept, so we can plot it. And to plot it, we use the abline command. And so on the school computers, we notice that you have to first run the plot and run the abline command, or AB line, I call it abline. You have to run them at the same time. For me, I can run them separately, but it just needs to have the plot available, and then it can plot the abline on top of it. And so if we run them together, because that's what you'll have to do on the school computers, you can just highlight both of them and hit Control Enter, or just run it all, and then it'll plot this line on here. Nice. So for your work, for your lab report, like I said, you're going to conduct one t-test appropriate to your data set. So you're going to set up a formal hypothesis test and state your conclusion. Same thing, do a proportion Z test, so prop dot test, and again, set up your formal hypothesis and state your conclusion. And then you're going to pull up that scatter plot that you made the last lab and construct a linear model for this relationship. So whatever relationship it is, I realize that because you've picked up your data set from different places, you might not have a straight line relationship. We're just going to go ahead and fit a straight line anyways. Okay. Which you'll see in my sample report that I posted. I don't have a linear relationship, but I just plow ahead and fit a straight line anyways. It's not going to be a good predictor, but it's just showing that you know what you're doing, or how to make a straight line, rather. So then you're going to print the summary of the linear model that you just made in step 3, and tell me what's the intercept, what's the slope, and what's the r squared value. And then finally add the line of best fit to your scatter plot. One quick note is that if we knit this, because you have to print off your lab report, and maybe you don't want to print off huge figures every time, I'll show you how to change the size of the figures. And so we've got this, all this work here, blah, 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 blah. And then down here at the bottom, right, if we want to change this figure size, in the chunk that generates your figure, so here's our plot command, up at the top here, you can change some options and say fig dot width. 3 is usually good. It doesn't take units, which is weird. It's just a magical 3. And because I want it square, I'm going to say that the fig dot height is also going to be 3. Okay. So just from before, it looks like this. If I knit this again, it's 3 by 3. Not sure what units, but it's smaller. Okay, so if you're making lots of plots and you're showing them and you think that they can be shrunk down a little bit, then go ahead and just shrink them down using this fig dot width and fig dot height argument. Okay. All right. Cool. I think that's all we've got. Well done. I guess you're done the labs. Congratulations.